Controlling a motor is the basis of any mechatronics and robotics system. Today, let's have a look on how to get started with PID control of a DC motor with encoders. We will use the following components. First, the microcontroller is an ESP32 development board. It is an affordable and powerful board that is highly accessible. We will use a motor driver called BTS7960, also called IBT2. It may be oversized for this project. Finally, we will use the GJB37520 motors with encoders. All the components should be easily available worldwide. For coding, VS Code and Platform I/O are the preferred tools. Arduino IDE is good to get started, but does not scale well as the project becomes bigger. This is our current setup with the 3 key components. Let's clean it up. The ESP32 is installed on a custom PCB. Breadboard is quite unreliable, so the use of a PCB or an ESP32 screw terminal breakout board is much more trustworthy. Then the IBT2 is placed on an acrylic plate. It's always nicer to have components well organized. Finally, the motors and the encoders. Please note that the motors include a gearbox with a ratio of 1 to 30, and the resolution of the encoder is 11 pulses per revolution. The output shaft of the drivetrain is thus 330 pulses per revolutions. A note on the connectors. Single DuPont connectors are usually loose and cannot be trusted. Because of the number of cables, it is much better to use connectors that are reliable. For the power supply, we use a barrel jack connector. For the DC motor connection, we use a GST-PH 2.0 connector. The GST family has several sizes of connectors, so be careful about selecting the right one. Then for the IBT2 to the ESP32, DuPont connector is used with a 2x4 on the IBT2 side and a 1x8 to the PCB side. The IBT2 is connected to the motor via screw terminals M1 and M2. It is connected to the power supply via the ground and the 12 volt. Finally, the logic signals is connected to the ESP32. Note that the IS pins are unconnected. The enable pins are connected to the 3.3 volt. On the motor side, the encoders are connected to the ESP32. It requires a power supply from the ESP32 3.3 volt, and the quadrature pins of the encoders is connected to the GPIO of the ESP32. After using spacers between acrylic plates and the PCB board, the mechatronic project looks this way, which is pretty and compact. Coding, we will use VS Code and Platform I/O. I would suggest you to download VS Code, which is free to use. Platform I/O is an extension that you can download within the VS Code environment. After installing Platform I/O, you can see the icon on the left-hand side. Select the icon, click Open and click New Project. One of the first files that needs to be modified is the platform io.ini for initialization. Please make sure that you are selecting the platform ESP32. The board is ESP32 dev. The framework used is Arduino. And then the tool library which is used is ESP32 encoders to read the encoders, and then the PID library. Make sure that you are using the monitor speed of 115,200 in order to communicate with the serial communication. The main code calls the other function, which consists of the PID controller, the encoder, the motor, and the serial communication. First, we initialize all the library. Then we initialize the object encoder, motor, and controller. In the Arduino framework, we have the void setup, which is starting all the functions like the encoder, the motor, the controller, and the serial communication. Then we have the void loop, where the code is repeated indefinitely. First, we are reading the encoder, then we are estimating the angular speed. After checking if the PID controller is enabled, we send the required PWM signals to the motor. We can read the data from the encoder through the function serial data print, and we can send some data, especially the desired angular velocity, through the serial data write. A MATLAB graphic user interface has been developed to interact with the mechatronic system. We will use this interface to change the desired angular velocity and the value of the PID controller. A quick reminder on the PID control system. A DC motor receives as an input a motor command in terms of PWM. It outputs the measured angular speed from the encoders. The PID is a function that is living inside the ESP32. In summary, you decide if you would like to have an aggressive behavior of the rotation of the motor or something which is a little bit more conservative. The desired angular speed is the data that you are sending from MATLAB. We're going to compare it with the measured angular speed, and the difference is going to be sent to the PID in order to correct the motor command. Let's have a look on the effect of P on the PID control. Here you can see that we have put a reference of 20 radians per second as a rotation. However, we can see that the angular speed is only 12 radians per second, so the error is quite large. We have increased the P gain by 200, but here one of the problems is the overshoot. By increasing the gain P, you can notice that the system becomes unstable. Now let's have a look on the effect of the I gain. Here you can see that the desired speed is 20 radians per second, and then we can achieve it with the I gain. By increasing the I gain, we can reach the desired speed much faster as well. However, increasing the eye gain leads to overshoot at some point. Similarly to the P gain, increasing the eye gain too much leads to instability. Let's have a look on the value of the D gain. You can see that the motor command signal is quite noisy. The D gain is normally used to attenuate the potential overshoot on the measured angular velocity. However, because the encoder has a low resolution, the D gain tends to amplify the noise of the sensor. You may notice that the PID gain are selected by trials and error. One topic of control system is to find the PID gain to optimize performance and stability. In conclusion, we have looked at different hardware in this project: ESP32, IBT2, TJB37. We have looked at some piece of the software: VS Code, Platform I/O, and MATLAB. We have an understanding of the PID effect. For the future works, we would like to know how to model our DC motors, which is called model identification. We would like to have a more rigorous PID tuning. And maybe we would like to explore more coding with VS Code and Platform I/O. And then finally, we would like to have a look on how to design your own app with MATLAB App Designer or Simulink. Thank you very much.